get, suppose this is some polynomial in the variable z. यस अर्पित, आपने अभी अभी ज्वाइन किया है। अर्पित, अर्पित, यस अर्पित, कैन यू हियर मी? अर्पित, अर्पित, क्लास मेरे ख्याल से आप समझ रहे होंगे क्या हो रहा है। क्लास आप लोग समझ रहे हैं क्या हो रहा है?
Yes, sir.
Okay.
Yes, sir.
I mean, without taking permission, I mean, it's really not good. Okay. So, polynomial in that. And so far as roots is concerned, you know that a complex number, of course, we are in complex field. A will be called root of pz class. You know that if the value of p at a vanishes. You know this. Right, class?
Yes, sir.
Okay, that is one thing. Secondly, class, all of you know division algorithm. From algebra. So you know that, class, suppose you have two polynomials pz and qz, and suppose then, class, you know that division algorithm says that you can talk of, for these given two polynomials, you can talk of another polynomials s sz and rz such that pz can be expressed as sz qz plus rz. Right, class? Here very often this the degree of this rz is greater than equal to 0 and less than the,
Degree of pz.
yes, degree of pz, right? Degree of qz, sorry, degree of qz, sorry, class, degree of qz. Okay, good enough. Which you may call as the remainder, let us say. So, class, take a note. If you have this situation, if a is root of p, class, then the value of r at a also turns out to be 1, class. Sorry, also turns out to be 0. You don't have any remainder. Am I right, class? And
Yes,
Yes,
sir.
sir.
and sir, and class, in that case, and in fact, what happens in that case? And in fact, and in fact, uh, this turns out to be a. This turns out to be a. Sorry, you know this. I'm not telling you something new. A factor of pz, right, class?
Yes, sir.
Right, and that is, we may write pz something like x minus a into qz, where, take a note, that this time degree of this qz is strictly less than the degree of pz, right, class? In fact, it will be,
सर Z आएगा ना?
where, class? Oh, sorry, sorry. In fact, class, the degree of qz will be strictly 1 less than the degree of pz, right, class?
Yes, sir. Yes, sir.
I mean,
Yes, sir.
all this you know, right? And class, suppose if we go on getting that again and again a is coming out to be root of pz, and suppose we are able to, or we lead to such a situation where pz is z minus a to the power m and q at a is not 0. So it means, class, that you can see that a is appearing as the root of the polynomial pz m times, where m is certainly a positive integer greater than equal to 1. Certainly it's an integer, but this a is not a root of q. So then class, we say, all of you know that, then this m is called as the class
Multiplicity.
Multiplicity.
very good, very multiplicity of the root a. Then we say that that the multiplicity of root a is m. Okay, good, good enough class. So class, um, not only this class, in fact, okay, and please class take a note. Here this will no more be actually it is qz. It will be something, some different polynomial. Sorry, I hope you are getting me. It will no more be qz. It will be some different polynomial, such that t of a is not equal to 0. It means a is not a root of tz. You go on doing this exercise, because qz will go on reducing by degree 1 every time, and every time you will be getting a different polynomial, right class?
Yes, sir.
Right, okay. Also class, take a note. Also class, take a note that this expression also tells us that degree of pz will be equal to m plus degree of tz. Am I right class?
Yes, sir. Yes, sir.
Yes, if a is a root of multiplicity m. So class, you can see that clearly, if degree of pz is m, it means, suppose you are given that degree of pz is m, then if I
Pizza
call it,
will be constant.
yes, very good, very good. Then uh, from 1, this tz must be a constant only, and class, uh, pz will be something like some constant into z minus e to the power m. Is this okay class?
Yes, sir.
Right, and then in such a situation, we say that we have completely factorized this pz into the uh, polynomials of degree 1. Is this okay class?
Yes, sir.
So class, let me tell you that it's an important consequence of fundamental theorem of algebra. This is actually class,
अरे क्या लिखा है लास्ट में into the polynomial of degree 1.
yes, oh sorry, uh, into the these and these into the when I'm saying these polynomials, I'm saying polynomial factors. Is this okay? Polynomial factors. Each of the factor here is of the type z minus a. Is this okay, class?
Okay, sir.
All right. So now you are in M.Sc. I mean, if I miss at some place, you may take a note of that. That what could that actually mean? The basics of mathematics, they are not going to change, whether you are at M.Sc level or you are at my level. The basics of mathematics, they remain the same. Anyways, class. So class, this is, let me tell you, is a consequence of the this complete factorization into the polynomials of degree 1 uh, is a consequence of fundamental theorem of algebra. So class, let me tell you that in this section you will be learning three important things. One is very important, what we call as the three important concepts of this chapter. One is the class, you will be learning about the Liverlees theorem, which in fact those who have done graduation from Delhi University, they have already done, but here I will be giving you a comparatively simpler proof. Number two, class you will be learning about the fundamental theorem of algebra. In this section, of course, fundamental theorem of algebra, which you know by now. I don't know whether you have done its proof till now or not, because one of the tools which it requires is the study of complex numbers. And I hope you know the statement fundamental theorem of algebra simply says that if you have a non-constant polynomial, then it will at least have one complex root, or one root in the complex field. That is the fundamental theorem of algebra. Right, class? And the third thing, something very important which you will be learning, is the maximum modulus theorem. So these are the three important theorems which you are going to learn in this section. So class, to begin with, first of all, I am going to define the zero of a complex valued function. I'm going to start with this. So very first definition. So suppose class, we have a function from G to C. Very often, unless until stated, this G is always taken to be an open set in C. This is open set in C. So class, suppose this function f is analytic. Then class, any A in G is said to be a zero of f if, I mean, this is something very usual known to you, that the point at which the value of the function vanishes. Is this okay, class?
Yes, sir.
And A is said to be a zero of multiplicity m greater than equal to 1, of some multiplicity m, and the value of m is greater than equal to 1, if there exists another analytic function g from capital G to C such that fz can be expressed as this, where the value of g at a must not vanish. If you see, class, this definition is almost in agreement with definition number 1. Yes or no?
Yes, sir. Yes, sir.
So if you allow me, let me call it number 2. So this is how we define a zero of a given analytic function having multiplicity. I mean, if the zero is having multiplicity m, then it means that fz can be expressed as z minus a to the power m into another analytic function for which this a will not be a root. Plus, there is another very simple definition, though there is nothing like definition in it. This you already know, and that is basically entire function. Class, all of you know what is the meaning of an entire function. Entire function means simply a function. Of course, we are talking of complex valued function, a function which is analytic on,
Entire complex thing.
yeah, on the entire complex plane. Good enough. So class, if you recall, last time I told you that an analytic function has a power series expansion, and that finally resulted into the fact that an analytic function is infinitely differentiable. Right, class? This I told you last time. Do you remember this? Yeah, I told you this. If f, yeah, it is here. It is then f is infinitely differentiable, and you are getting this infinite differentiability because of the simple fact that you could write this f in terms of a polynomial of infinite degree, and because you could differentiate that infinite number of times, and hence you get the infinite times differentiability of the function f. So the similar thing we can say about the entire function, because entire functions are in no way different from the analytic functions. The only difference is that now they are analytic on the whole of complex. That's the only difference. Otherwise, there is no difference between an analytic function and entire function. So class, in this direction, I am giving you this result, which actually I have already explained you for analytic functions. And likewise, you can explain it for the entire functions also. I will give you just a short explanation for that. Okay. So the result is this, class. Let f, sorry, let f be an entire function. So class, needless to say that the let sorry, let f, अरे भाई क्या हो गया? So class, needless to say that the domain of f is
C.
yes,
C.
good. Then if f is entire function, then f has a power series expansion of this type. This I have already explained you yesterday for analytic functions with radius of convergence equal to. So class, what do you expect to be the radius of convergence of this series?
Infinity.
Yes,
Infinite.
yes, infinity, yes. Because now this should be available to you for each and every complex number, right? Equal to infinity. Good. And so far as the explanation is concerned, class, the explanation is quite simple. There is nothing like proof in it. So, class, uh, let us consider uh, a ball in C. Take any point. I mean, this is understood that A is any point in C and R is certainly within 0. Take any ball. Then, class, needless to say that F is analytic on BAR, right, class?
Yes, sir.
In fact, rather than taking BAR, class, why don't you take simply this? That's it. So you can even remove this. So you just take this ball. So clearly F is analytic on this ball because it is given that it is analytic on the all of the complex plane. And class, we can write Fz is equal to summation an z to the power n is going from 0 to infinity. I hope you are getting that we will be getting this from where? From theorem, that very important theorem, that was theorem 2.8. Is that okay, class? By theorem 2.8, which tells us about the existence of power series expansion for an analytic function, right, class?
Yes, sir.
Yes, sir.
Yes, sir.
In fact, yesterday I did a corollary also, you can consider that also. And fz is equal to this, and this must be for all z such that mod z is less than r. It means mod z is less than r means for all those z's which are in this ball. For each one of those balls, for each one of such points, you must be able to write down this series expansion for fz. And class, you know that moreover, class, you know that the radius of convergence of this series will be at least this r. It means it will be actually radius of convergence will be greater than equal to r. Is this okay, class? You know this from that theorem,
Yes, sir.
Yes, sir.
right? And class, now here this r is arbitrary. Is this okay, class?
Yes, sir.
So combining these two things and letting r tend to infinity, it follows that fz is equal to summation an z to the power n is 0 to infinity for all z in the complex plane. Is this okay, class?
Yes, sir. Yes, sir.
So the series of the radius of convergence of this series is infinite automatically. Good enough. Now, so class, one more thing which we can see from this expression, let me call it number 3. So if you notice this series on the right hand side of the expression 3 is nothing but a polynomial of infinite degree. Yes or no, class?
Yes, sir.
Yes, sir.
Right? And this polynomial of infinite degree is infinitely differentiable, and hence the function f is also infinitely differentiable. Yes or no, class?
Yes, sir.
Yes,
So
sir.
I can simply say every, now this is, you can say some sort of observation. Every entire function, or you can say simply n means every, an entire function is infinitely differentiable. Now class, take a note that what tool I have used to draw this observation. I have used the fact that the right hand side, this was a polynomial of infinite degree, and I could differentiate it infinite number of times with respect to z. Yes or no, class?
Yes, sir.
Of infinite degree. So it means, in a way, I am trying to say that this is a property of entire functions, the property of infinite differentiability, which is in fact, I can say, is inherited from the polynomials in some sense, and it is possible because of this very fact that we are able to write a power series expansion for an entire function. Right, class? So this property of infinitely many times differentiability of a polynomial, if we have a polynomial of infinite degree, this ultimately leads to the infinite differentiability or infinite times differentiability of an entire function. So this property, in fact, comes into the entire functions from that of polynomials. ऐसा नहीं लग रहा क्लास? क्योंकि एंटायर फंक्शन, डिफरेंशिएबल फंक्शन, इन सबसे पहले तो हम किसको जानते हैं क्लास? 9th क्लास से 10th क्लास से वी नो अबाउट पॉलिनोमियल्स. राइट क्लास?
Yes, sir.
Yes, sir.
Yes, sir.
ओके क्लास. तो क्लास, बड़ी अच्छी बात लगी कि पॉलिनोमियल्स के बारे में एक ऑब्जर्वेशन हम जानते थे कि अगर इनफाइनाइट डिग्री का पॉलिनोमियल है तो उसको इनफाइनाइटली मेनी टाइम्स डिफरेंशिएट किया जा सकता है. तो हमने देखा कि एंटायर फंक्शन में भी हमें वो खूबी मिली. ठीक है क्लास? ठीक है. अब क्लास पॉलिनोमियल्स के बारे में हम एक और ऑब्जर्वेशन लेते हैं. लेट अस take, okay, let us take an observation about polynomials. You see, I am going to take another observation about polynomials, class. Class, another observation about polynomials is the following. This is a very important thing, that no non-constant polynomial is bounded. Right, class?
Yes, sir.
Yes, sir.
Is the same thing you can say like this, class, or if a polynomial is non-constant polynomial can't be bounded. If you have a non-constant polynomial, it can't be bounded. Or you can say it this way also. That if a polynomial is bounded, then it must be constant. Class, I would like to say one thing. I am making all this discussion on, this is very important, I am making all this discussion on C. So if on C, if a polynomial is bounded, then it must be constant. They are one and the same thing, class. So let me explain this to you, class, this observation. And class, then I will show you that this beautiful observation is being enjoyed by the entire function also. Okay, good enough. So I can explain it like this. Suppose, class, we have a polynomial pz. Suppose we have this. A non-constant polynomial means, class, something like this. Right? Let us say its degree is n, and an is non-zero. Degree n means an is non-zero. And class, take a note, we are talking on C. Because now my concern is the entire functions. So, class, you can see that if I take limit z tending to infinity of pz, then class, this will be further equal to limit z tending to infinity. You take z to the power n common. So class, if you take z to the power n common from this pz, then class, you will see that you will have something like this: an minus 1 upon z plus an minus 2 upon z square plus dot dot plus a naught upon z to the power n. Yes or no, class?
Yes, sir.
Yes, sir.
Right? Now, class, as z tends to infinity, what will happen to all these terms? They will
Zero. Zero.
vanish. All right. Class, please take a note. When we say z tending to infinity, please take a note. This is if and only if mod z tends to infinity. So saying a complex number is tending to infinity means you must be clear about its meaning. It means it is getting away, and away from the origin. Is this okay, class?
Yes, sir.
Yes, sir.
So each one of them will go to 0 and you will be left with an only. An is non-zero. So when z goes to infinity, ultimately you will get plus infinity. Is this okay, class?
Yes, sir.
So this is I was trying to tell you that if it is non-constant, if it is a non-constant polynomial, then it can't be bounded. Please take a note. I am talking on C, so it can't be bounded on C. Ultimately, you can see that as z becomes very very large, the polynomial explodes. Is this okay, class?
Yes, sir.
Class, let me tell you that the same property is being enjoyed by entire functions. So I will mention the statement about the entire functions parallel to this third statement. So if we have an entire, instead of polynomial, if we have an entire function and it is bounded, then it will be
Constant.
Constant.
yes. And class, do you remember what is that?
Livolis theorem.
Very
Theorem.
good, very good. That is the Livolis theorem. So class, if f is entire and bounded, then this implies that the theorem says that f must be constant. Is this okay, class?
Yes, sir.
Class, take a note. There is no theorem parallel to this theorem for real valued functions. You may have a real valued function which is differentiable on the whole of real line, which is bounded but is not constant, right? You may have a real valued function which is differentiable on the whole of real line, which is bounded and is not constant. Can someone of you tell me such a function?
Sin x.
Very good. Sin x, very easy. Good. Also, class, this is a very good result which tells us that sin z is bounded. This result tells us that sin z is bounded. Because, class, the logic is very simple. Sin z is entire, we know this. Sorry, is
Unbounded.
Unbounded, sir. Na?
is not bounded. Sorry. Because we know that sin z is entire, and on the contrary, if it is bounded, then by Livolis theorem, it should be
Constant.
constant, which is a contradiction. You know that sin z is not constant. You change z, the value of sin z will change. Is this okay, class?
Yes, sir.
So a very simple and beautiful application of Livolis theorem. So class, let's look into the proof of the Livolis theorem. Very simple proof. So class, it is entire and bounded. It means class, sorry. Proof. So class, you know the meaning of bounded. It means there will be some capital M greater than 0 such that mod of fz is less than equal to m for all z in C. Is this okay, class?
Yes, sir.
Now, since f is entire, it is analytic in bz comma r for all z in C and for all r greater than 0. Meaning thereby is that class, you take any arbitrary ball in C, this function will be analytic on that. Is this okay? Because the function is analytic on the whole of the complex plane, right? Is this okay?
Yes, yes.
Okay, good enough. Now class, you recall the Cauchy's estimate. That was theorem, I mean that was, what was the Cauchy's estimate class? This was the Cauchy's estimate. Cauchy's estimate. This was actually 2.14 at page 73 of your book. And this Cauchy's estimate says class that if f is analytic on a ball and suppose it is less than equal to m for all z in this ball class, then if you remember, Cauchy's estimate tells us about the bounds of the values of nth derivatives of the given function at this point a, at this point a, and it tells us that this will be less than equal to m times r to the power n.
N factor.
Very good, very good. This is for all n. Is this okay, class?
Yes,
Now,
sir.
now if you notice, our function is satisfying this condition as well as this condition, because a mod of fz is less than equal to m for all z in C. So in particular for all z in this ball.
Yes, sir.
So therefore by Cauchy's estimate, therefore by Cauchy's estimate, for n is equal to 1, we are going to apply the Cauchy's estimate for n is equal to 1. We have, what would we have, class? F dash
Z.
at z, because our center is any arbitrary z, and its modulus is less than equal to m upon r. Is this okay, class?
Yes, sir.
All right. And class, take a note. This is for all r greater than 0, because there was no binding on r or on the choice of z. And the reason being is that our function is entire. So we could take any ball centered at any point in the complex plane, right?
Yes, sir.
So therefore, letting r tend to infinity, making it as large as possible, we have mod of f dash z is less than equal to 0. And class, you know that modulus is always by default bigger than greater than equal to 0, right, class?
Yes.
And
Yes, sir.
class, take a note. This is for all z in C, right? This is for all z. There was no restriction on these jets. Is this okay, class?
Yes, sir.
And class, it means what? That is, this implies that f dash z is equal to 0 for all z in C. Because class, you know that if you have a some complex number, then its modulus is 0 if and only if the complex number itself is 0. Is this okay, class? So I have used this fact. And class, it means what? If it is for all, yes, if it is for all z's, then it means it is constant on C. And hence done. Is this okay, class? Very nice and simple proof. Is this okay, class?
Yes, sir.
Yes, sir.
Now, class, I am going to make use of this the Willis theorem, a very important result, to prove next important result. What is?
सर इसका कन्वर्स भी ट्रू होगा.
If it is constant, then it is trivially entire and bounded. A constant a constant function is trivially entire and bounded. So the converse is trivially true. Yes or no?
Yes, sir.
Mhm. Okay. Fundamental theorem of algebra. And let me give you its statements first. So if Pz is a non-constant polynomial, then there is a complex number a such that the value of value of p at a will be 0. It means this a will be the root of this polynomial. It means simply I am saying that every non-constant polynomial in Z will have a root. Is this okay, class?
Yes, sir.
So let's write the proof. So we will start with the contrary approach. So let us take some polynomial. Let Pz be, let us consider, I can write like this. Let us consider this polynomial. Let us take a polynomial of nth degree in Z. Okay. Of course, this n is greater than or equal to 1. Why, class? Because we are considering
Non-constant.
yes, good. Okay. So we will start with the contrary approach. So we will assume, suppose it has no root in C. Okay. On the contrary, suppose there exists no A. Okay, there exists no. Okay, you can say A in C such that PA is equal to 0. Anyway, I am saying, class, that is PZ has no root in C. Is this okay, class?
Yes, sir.
That is, it means, class, the value of P at any complex number cannot be 0.
0.
Is this okay, class?
Yes, sir.
It has
Yes.
no it has no root means whatever complex number you take, the value will be non-zero. Is this okay?
Yes, sir.
And
Yeah.
class, now you are in semester 1 M.Sc. You must be getting an idea that whenever you claim or project something to be non-zero, it means you are somewhere going to make use of that in the
Denominator.
very good, right? So let us consider a function fz defined like this. Then clearly, class, since Pz is analytic in C, yes or no? If a polynomial function is analytic in C, it is entire, and this is just constant function. So using the algebra of analytic functions, I can say clearly f is analytic in, or yes, you can say entire is analytic in C, or you can say entire. Is this okay, class? Clearly meaning the meaning of clearly is okay.
Yes, sir.
Okay, fine, good enough. Now, note that limit z tending to infinity of Pz, class, as I explained you just 10 minutes ago, the limit of pz as z tends to infinity will come out to be infinity if it is, because we are taking a non-constant polynomial, right class?
Yes, sir.
Yes, sir.
Yeah, I explained you it in the beginning today. Yeah, it is here. Is this okay class? So note that as z tends to infinity, this limit will be infinity. And it means what class? Therefore, limit z tends to infinity of fz will be what class? This will be,
Zero.
0.
yes, it will be 0. And now class, let us simply use the meaning of limit. So it means class that this implies that for a given epsilon greater than 0, there exists r positive such that mod of fz will be less than epsilon for all z such that mod z is greater than r. I hope class you know the meaning of when we say that z is tending to infinity. It means if you go on making z larger and larger, it means after a certain stage, if you take z's, then mod fz will become less than epsilon if the limit is 0, right class? Basically here it is minus 0. Is this okay class? I have simply used the meaning of limit at infinity. Is this okay class?
Yes,
Yes, sir.
sir.
Clear.
Yes, sir.
Yeah. Okay. So I mean, I'm not very clear about the students, those who have done graduation outside Delhi University, but those who have done it from Delhi University, I still remember that it was given in chapter 2 of Brown and Churchill about the limits at infinity and infinite limits for complex valued functions. Okay, good enough. So class, this is for any given epsilon greater than 0. So in particular, let epsilon be equal to 1. Then for this also, then there exists some r. I'm saying this r will depend upon this choice of epsilon. Na? This r is depending upon the choice of epsilon. So I will be having some r. Let me say it r1 class, such that mod of fz will be less than 1 for all z such that mod z is greater than r. Is this okay class?
Yes, sir.
So let me say it number 1. Good enough. Now class, consider the ball B0, R1. Class, take a note. This is R1 and here also I am taking the same radius. I am doing it purposely. It will be clear to you within a minute. And I am taking the corresponding closed ball. It is not the closer. Please take a note. It is the closed ball centered at origin having radius R1. So basically class, just for the sake of understanding, basically this set is what? This set is the collection of all those complex numbers in the complex plane such that mod z is less than equal to R1. Is this okay class? This is how we define closed ball. Anyways, so consider the ball this. Then since f is entire, this implies that f is continuous on C. Entire means continuous, right class? Entire means analytic, analytic means continuous.
Yes, sir. Yes, sir.
Continuous on C and hence on. So it will be continuous on this also class.
Yes, sir.
And now
Yes, sir.
this is closed and bounded, a compact set in C. Now this is a compact set in C class. C endowed with usual metric is a metric space. And class, you know it from your graduation that every continuous function defined on a compact set is bounded. Right, class?
Yes, sir.
Yes, sir.
So therefore f is bounded on this. And class, what is the meaning of bounded? That is, there exists some m greater than 0 such that mod of fz will be less than m or equal to m for all those z such that z belongs to this ball. Yes or no, class? Right?
Yes, sir.
Or
Yes,
instead
sir.
of writing this, you can write all those z such that mod of z is less than equal to r1. Is this okay, class? Is this okay, class?
Yes, sir.
So call it number 2. So class, now you can see something very interesting. So if you take radius r1, it is this ball, it's closed. So at every point of this ball, inside this ball, the function is being controlled by m, and outside this ball, when mod z is greater than r, the function is being controlled by
1, sir. 1.
1, right? So ultimately you can see that the function is controlled on the whole of the complex plane. Yes or no?
Yes, sir.
Less than equal to r1 you are covering here, and greater than r1 you are covering here. Where it is r1, sorry class, it is r1. Yeah, r1. This is right. So class, now I'm going to conclude it. So let m dash is equal to maximum of m comma 1. Is this okay, class?
Yes, sir.
And you can talk of the maximum of two numbers, there is no problem in it. Then from 1 and 2 we have mod of fz less than equal to m dash for all z in C. Is this okay, class?
Yes, sir. Yes, sir.
Yes, sir.
This implies what? That f is bounded on C.
Yes, sir. Yes, yes, sir.
But f is already entire on C. If you remember, f is entire on C.
Yes,
Yes
sir.
or no? F is entire on C. You see, right? So it is entire, and I have shown that it is bounded. Therefore, by Livolli's theorem, f must be
Constant.
constant. That is class 1 upon pz. What was fz? Fz was 1 upon pz.
1 upon
It
PZ.
means
1
this
upon
must
PZ.
be constant, right? Is this okay, class?
Yes, sir.
And this is a contradiction, class. This is a
Yes,
contradiction because this is possible only when pz is constant. But you know that pz is not constant. So certainly this overall thing can't be constant. Yes or no, class?
Yes, sir.
Which is a contradiction since pz is non-constant. And therefore, class, what? Therefore, we start with something contrary. This supposition. Therefore, our this assumption goes wrong. Right, class? Therefore, our supposition goes wrong. And hence, there exist at least one A belonging to C for which EA will be 0. Yes or no, class?
Yes, sir.
And this completes the proof. So, how was it, class?
So good.
Nice.
अच्छा था सर.
Okay. So, class, we will stop here. But before I stop, I would leave you tempting a little. Just a minute. So, class, today I showed you two things about the entire function, which it seems to carry from the polynomials. One was that a polynomial of infinite degree is infinitely differentiable. So we observe that entire functions also enjoy that kind of thing. Now, second was that about the polynomials, uh, we have an idea that uh,
If polynomial is bounded.
yes, every non-constant. I mean, if a polynomial you have a non-constant polynomial, then it can't be bounded. So if you have a bounded polynomial, then it must be constant, because a polynomial is by definition, I mean by default, it's infinitely differentiable. So you can see that that property is also, I mean, that kind of phenomena is also carried by entire functions. If you have an entire function and it is bounded, then it must be constant, right, class? Then a very natural, I mean, something very naturally comes to our mind, that uh, are there some more things, or is it so always that the properties or the phenomena which we observe with the polynomials of infinite degree, of course, you can say, or even polynomials, if you are considering them on the entire plane, that they are being observed by the entire functions also? Are there some more properties, or are most of the properties of polynomials being enjoyed by the entire functions? So this kind of question comes to our mind, looking at these two phenomena, where entire function is carrying some feature from the polynomials. So class, tomorrow I will be starting with this, that prima facie it appears to be so, but actually we can't continue with this uh, too far. So I will be starting tomorrow with the example where I will show you just a very simple property, which is being enjoyed by the polynomials, but not being enjoyed by the entire functions. Right, class? So let me stop over here, and you just give me a few seconds to take your attendance. Okay, class. Thank you very much. I have taken your attendance. We will connect
Thank
tomorrow.
you,
Thank you
sir.
very much.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Okay.
Sir, excuse me, sir.
Yes, Ayush.
Thank you, sir.
You have
Okay.
asked one question yesterday that give an example of a function that is. Sir, is my voice clear?
Yes, Ayush, it is clear. Yes, go ahead.
Sir, you have asked the question yesterday, sir. I want to just confirm the answer from you.
What was the question?
Sir, entirely so function which is continuous f and f dash exist, but f double dash does not exist in real life.
Okay. So, is it possible if you can WhatsApp me that, you just write that and click and then WhatsApp to me?
Yes, sir. Sure, sir.
So that will save our time. Okay.
Okay, sir.
Raj,
Thank you.
thank you. Thank you. You just WhatsApp me that. Okay.
Okay, sir.